I'm Professor Reis from Instituto Superior Técnico in Lisbon, Portugal. And I'm going to present this work, Mitigating Interfering Modes in Cruciform Specimens for Reliable UFT, a finite element under the EIC approach. So this work was performed by Professor Diogo Montalvao, Sina, and Weston from the Department of Design and Engineering in UK. And from Lisbon, we are three co-authors also, Dr. Pedro Costa, myself, and Professor Manuel Freitas. This is the outline of my presentation. I will start with a brief introduction of objective of in-plane biaxial EFT with cruciform specimens. Then I'll move to the influence of nearby mode shapes. Then I'll talk about redesigning the TT specimens. And I will show some analysis of these new ones, TT specimens, and I will conclude with some remarks. So just a brief introduction and the objective. So we know that in most cases, the real surface loading conditions, we are running under biaxial stress states. And in particular, in plane biaxial stress states, as is these two well-known examples. Okay, so the objective of the main research of our group is to characterize, let's say, the materials under different regimes and also under different biaxial loading stress states. So it means we are considering biaxial tension for first quadrant, biaxial tension compression, second and for the third one, compression. So in this case, we are going to perform very high cycle fatigue tests in particular with these cruciform specimens. So, but all this work started with, in the beginning with our machine, with this machine in plane with 4 independent linear electric engines, as you can see here. And the capacity of this machine is around plus minus 3.5 kilonewtons, a maximum displacement around 85 millimeters, and a maximum frequency in the uniaxial conditions around 100, and in case of biaxial conditions, 20 Hertz. So, we should also know that we use a simple USB microscope to monitor the center of the specimen here, the cruciform specimen here. And with this simple microscope, we can also detect the crack initiation and monitor the crack propagation. This type of specimen, the cruciform one, follows a specific geometry that should be optimized in order to assure that in the middle we have low stress concentration, as you can see by the colors. So we can pick here some orange-red colors, which could lead a failure of our test. So we should be very careful when dimensioning this type of specimens. And of course, we should assure that in the middle, in the center of the specimen, we have a uniform stress state to validate our test, our crack growth, and so on. And of course, doing this, we have all the conditions to follow the crack growth and to obtain, I don't know if it works, no. Can you show us the movie? Just click, yeah. So in this way, this is just for demonstration, we can obtain, it's not running. Yeah, okay, so sorry. That's why I want to use my computer. Okay, so, but with that, we can obtain the crack length versus the number of cycles, in this case, for in-phase loading. And in this case, in the second case, for the out-of-phase loading. So we are able to monitor the crack length versus the number of cycles. And in this way, we can also compute the crack growth rate. Okay, so this is for, let's say, fatigue conditions, not in very high cycle fatigue, but as you know, so the cruciform specimens have been the preferred method for in-plane axial fatigue, as are demonstrated here by other authors, using this type of specimen to perform in-plane biaxial fatigue. So, keeping in mind the resonance principles of use it in our machine, in our equipment to perform this type of test in very high cycle fatigue. So we consider the piezoelectric actuator and then the booster and the horn as working as mechanical amplification of the signal. And in the tip, we have the cruciform specimen that we are going to obtain a transverse axial motion and also a longitudinal one. So we can use also this type of specimens in these conditions to obtain the so-called biaxial TT. So we are going to call here when all the arms are stretching the TT mode, let's say, and when we have shear in the out of phase mode, as you can see here, these two arms are stretching, these two ones are shrinking, and we obtain the CT mode, we have shear. Let me also underline this. So with different arm lengths, we can produce different biaxiality ratios. So in this slide, I just want to show the different biaxiality ratios that we can produce, taking into account the different Bs. So we have performed the complete model analysis of the set, let's say the booster, the horn, and the specimen. And for the first case, we have equal 1. It means all the 4 arms are stretching at the same time. So we are here. And here we have the pure shear. So it means that 2 are in the out of phase loading. So 2 of them are stretching, the other 2 are shrinking. And while the third and fourth case, we have a B greater than 0 and B different 1. And the last one, we have a B lesser than 0 and a B different minus 1. So in this way, we cover all the spectrum, all the quadrants. Okay, so moving now to the influence of the nearby shapes. So regarding the out of phase loading, we have achieved very good results, very predictable results. So as you can see here by demonstration from this specimen here, so at the end, we can measure here a crack initiation angle around 45 degrees. So the things run perfectly and we reach very good results. Well, regarding the in-phase case, when we are in the phase loading, so all the arms are stretching at the same time, we face some issues. And the spurious mode shape appears here around the 20 kilohertz. So we have used lasers in different points of the arms just to check what happens. And well, the results were not so good. So we need to do something. Why this happened was the first question. And well, some reasons found included. So the first one should be related with the, well, we need to create a stud here with a M6 mounted thread, okay, just to attach to the horn. So could be related with this. The second reason could be also when we perform the attach to the horn to the specimen, so due to the boundary conditions. And also the third one, the existence of the mode with a close 9.6, which within the work range of the piezoelectric. This is related also with the type of loading that we are applying. So in this case, this is not related with the CT specimen. That's why I have obtained very good results, but is related with the tension specimen. So, and the result is a kind of this. So we are, let's say, the flapping of the arms when we apply the TT specimen loading in phase. So, well, we need to do something, how to solve this, and I will move to the third case. So the goal here is to shift the flapping mode to prevent interference at 20 kilohertz. So ensuring that the peak at this frequency is primarily due to the intended mode shape rather than the mix of 2 modes. So it means that we should decrease or increase the flexural frequency, and at the same time, we should keep the axial frequency, of course. So how to solve it? Well, our proposal is this one. So if we consider a massless beam, as is presented here for both cases, tension and bending, and then if we move the mass at the tip closer to the center, so it means that we are decreasing length L, we are going to increase the flexural frequencies by a factor of power 3/2 when compared to axial frequencies, okay? So what does it mean? It means that at the same time, we should assure that proportionally to bring the axial mode to 20 kilohertz. So in this way, we can compute the new mass that we need to take into account this movement from the tip to the center, towards the center of the tip mass. Okay? So this is the new sample. And in this case, we have produced it from the aluminum alloy 682 with the heat treatment T6 with the 2 millimeters of the tip masses, as you can see here. So here, change the thickness in all 4 tips. And then, well, from this, we have increasing the frequency from 19.6 to 22.7. Okay, so we shortened the specimen, as you can see from here to here a little bit, but we, at the same time, we increase the mass at the tips. So moving to the analysis of the new specimens, well, we carried out model and the harmonic analysis, and as you can see here, this is the mode of interest. Okay, so this is far. Also, the flapping mode is far from the 20.5, so it's out of the working range. And well, also the harmonics are very good. So the mode shapes running the simulations in ANSYS, well, the mode shapes are sufficiently spaced away, and also the maximum strain stress appears here in the center as we wish. So, but that's not all. So when we go to the lab, so another issues arise. So in this case, the IC show the transient mode, which is represented here by the green color. When it appears, you can see, well, there's a weird, let's say, behavior of the specimen. It's a kind of dance. So this is due to this transient mode. Again, it's not okay. So we need to do anything else to improve this behavior. And I'm going to move because I don't have time. So we shortened again the length of the thread connecting through. And we also added the bee walks between the horn and the specimen surfaces. So with these 2 issues, let's say, we move from here. This is the behavior of the horn, and we have a very good connection at the end. So after that, well, we run again several tests. And as you can see here in this table, so we obtain a very good, strong correlation between the input simulation and the experimental results from the laser and from the DIC. So from 2 experimental, let's say, methods, we obtained very good results. Well, there's a little difference here in the vertical axis, but not is negligible. Okay, finally, well, at the end, we can correlate the strengths here in the center of the specimen. That's what we want, with the tip displacement in both in horizontal and vertical axis. Okay, we also use in some samples, we also do some strain rosettes here in the middle just to confirm, just to achieve the strength at that point. Okay, final, just me highlight 3 issues. So one of them regarding the specimen design. So biaxial specimens should be designed to minimize the excitation of adjacent modes. This is very important. Another one is the mode coupling. So minimize mode coupling and non-desired modes. So this is very important. So we should use finite element and, of course, the IC analysis to address these issues. And finally, the connection regarding the connection design. So choose connection methods in order to avoid impacts and transient modes. Okay, I will finish. Thank you very much for your attention.